information about temporal distribution of such events, but their problem comes from the uncertainty that comes from lateral boundary and initial conditions, as well as due to large temporal and horizontal variability of convective processes. From this reason, we have tried an alternative approach to combine outputs from numerical models and rain gauge records. More specifically, we used model Cosmo with a horizontal resolution of 2.8 kilometers and temporal output of 10 minutes. The integration started at midnight and ended at plus 30 hours of LED time. So the first 6 hours were used as a spin-up time, so we used reforecast with a LED time of 6 to 30 hours in this study. For the temporal reconstruction, we also used rain gauge data that recorded the precipitation sum, daily precipitation sum, since 6 to 6 UTC of the next day. And you can see that the temporal distribution of rain gauge records well covers the area of the Czech Republic. For verification purposes, we used radar reflectivity data from two radars, Bdy and Skalky, with a temporal resolution of 10 or 5 minutes and horizontal resolution 1 kilometer. The suggested correction procedure was tested and evaluated on 7 selected events that occurred over the area of the Czech Republic since 2002 until 2013, and they include both predominantly stratiform as well as convective precipitation. All of them caused serious material and infrastructure damages and claimed several casualties. There is an overview of the proposed procedure that consists of 3 steps. In the first step, daily rain gauge point measurements and 24-hour model precipitation sums are used to obtain a 24-hour adjusted precipitation sum using the same adjustment procedure as in case of weather radar data adjustment. In the second step that takes place in a parallel way, we use a correlation coefficient between interpolated rain gauge observation and 24-hour model precipitation sum in a moving window. For each, the model field is shifted pixel by pixel in the north, south, and east-west direction, and compared with interpolated rain gauge field. For each model shift, we calculate the correlation coefficient from model pixels that are within the area of the Czech Republic, and the shift with the highest value of the correlation coefficient that determines the final direction that is finally applied to all 10-minute precipitation totals. Finally, we accumulate those 10 minutes in 24 hours and compare those two sums to get the ratio that is then used for multiplication of all 10-minute shifted precipitation totals. So in this way, we get 10-minute reconstructed precipitation reforecast and their 24-hour accumulation. This is an animation of reconstructed 10 minutes precipitation from 24th of June 2009. That's the right panel, compared with raw model observation and raw model forecast and observations. During this event, a heavy convective precipitation hit the east part of Moravia, and the raw model actually wrongly forecasted this event. The model forecasted this event more west compared to the observation, but what is important that this forecast was well captured in a temporal way, in a temporal point of view. So this is important for the correction procedure that can utilize and transform this information closer to the observation. There is another example of the event occurred on 7th of August 2010 that hit mainly the north and central parts of Bohemia. Again, the raw model shows that precipitation was reforecasted more west compared to the observation, and especially the north part of the Czech Republic was heavily underestimated. On the other hand, the corrected model seems to match better with the observation in the morning and early afternoon hours when we observe the highest precipitation. Here you can see a correlation difference between Pearson's correlation coefficient for corrected and raw 10-minute precipitation reforecasts. Full lines that are located above zero represent higher values of correlation coefficient for corrected reforecasts. On the other hand, the negative values means a deterioration of corrected reforecasts, so the raw model is better here. In addition, a relative time cumulative grid box average precipitation is depicted by dashed lines, and the asterisks on these lines delimits the times of the highest precipitation within a given event. These times were defined as the first and the last time of the occurrence of 10-minute precipitation totals equal or exceeding 75th percentile of all observed 10-minute precipitation. As you can see, a temporal distribution of this correlation difference varies during each event, but predominantly the corrected model is better. This feature is especially noticeable for two presented cases, 24th of June 2009, that's the green line, and 7th of August 2010, that's the blue line. Also, this improvement is not so obvious for other events. We can still see that there is still some improvement in times of the highest precipitation. The only event where we couldn't see any positive effect of application of this procedure was 12th of August 2002, because the original model already reforecasted well this heavy precipitation. So these two fields didn't differ significantly. We also verified the presented procedure using fraction scale score, whose main goal is to express the forecast quality on the dependence of the forecast quality on spatial scale. We used two thresholds, two absolute thresholds and two relative thresholds. The relative thresholds were calculated as a half or full 95th percentile of all observed 10-minute precipitation in a given domain. As you can see, the corrected model, which is the full lines, are better in all thresholds compared to raw reforecasts. Just to mention that this scale means 0 complete mismatch and 1 is perfect reforecasts. So let's go to summary. An alternative correction procedure for a posteriori improvement of quantitative precipitation reforecasts generated by model Cosmo in a high temporal resolution has been developed. The procedure adjusts the model precipitation sums by daily rain gauge measurements and corrects the localization of 10-minute model precipitation based on the highest correlation coefficient between the 24-hour model and daily observed precipitation sums. The results show that the model Cosmo usually well predicts the occurrence of events, but its spatial localization is not always accurate. This is usually the case of more localized convective precipitation, where the impact of correction procedure is the most evident. A detailed temporal analysis showed an improvement when the highest precipitation within a given event occurs. In case the raw and corrected reforecasts do not significantly differ, the impact of the procedure is rather negligible. Although the results stem from the 7 selected cases only, the study indicates that the method can be applied to historical events for which no weather radar data are available. So, yeah, thank you. Yes?
So somehow I don't realize that. So how do you do this correction in real-time operation?
This is not supposed to be for real observation. This is for reforecasts. It means for the historical events. It's not supposed to be online.
Okay, so it's more like a...
Yeah, it's a reforecast for historical events. So we want to study the temporal distribution in a high resolution for historical events where we don't have the observation data.
How do you deal with the fact that the model outputs change during different model runs? For example, early in the morning, 6 o'clock model run, there's another forecast at noon.
We used only one, yes.
Always the same?
Yes. It's the same that starts at midnight for every event presented case study.
Do you try short-term time period for the gauge? How do you, instead of daily? Would you try to
no, because we don't have data in higher temporal resolution for rain gauges for historical events.
Simply because you don't have it. But if you had it, would you try shorter time?
Well, if we have it, we don't need to do all this stuff because we have the observation. Okay. All right.